Today we're going to learn about something called the limit definition of the derivative. But where this really comes from is one of the two big problems that motivated the creation of calculus. And the first one is the tangent line problem. In earlier maths, you've certainly learned to find slope between 2 points. And you've pretty much always found the slope of a straight line. But with calculus, not only can we find slope using just 1 point, we can find the slope of curved lines. So I want you to consider for a second a curve. Just use a parabola. The reason this is more complicated than your slope previously was that the slope is constantly changing. If you consider the slope right here, for example, that's a negative slope. We know that because the function is decreasing right there. Right here we would probably have a slope of 0 because it's very flat right on the bottom. And then over here we would have a positive slope. Now the reason they call it the tangent line problem is because it turns out that the slope at those points is exactly the same as the slope of a tangent line to that point would be. So a tangent line is a line that touches exactly one point. And it doesn't cross through, it just touches and then passes by. So the slope of that red tangent line I drew will be the same as the slope at that point that I just pointed to. Same thing for any of these dots. If I draw the tangent line at those dots, they should have the same slope as the slope at that point. So they really were just trying to figure out how do we find slope at a single point. So let's talk about that. How do we find slope at a single point? Well, I just labeled this 1, 3, just kind of made this up so we had some numbers to work with. And I want to be able to find the slope of the tangent line to that point. The problem is, I don't know, at least up to this point, and without calculus, I don't know how to find slope unless I have at least 2 points. Well, in calculus, one thing you'll learn that they did when they were trying to figure these things out is they said, okay, it doesn't appear, at least with what we know so far, that we can find these things absolutely. In other words, exactly. But we could approximate them. So this is one thing they tried. They said, okay, how about we go ahead and use 2 points? Here's the point 1, 3. Why don't we mark the point at 2, 5, and then draw a line through those 2 points. So this is not a tangent line. It's actually called a secant line when it hits 2 points. But if we could find the slope of that line, the black line I just drew, because it has 2 points, 1, 3, and 2, 5. So we could use the slope formula, find the slope, and then we would at least have an approximation. The slope of the black line is certainly not going to be the same as the slope of the red line, but they would at least be in the same ballpark. So that would be one way to approximate our slope. Well, they said we need to get more accurate than that. So if you want to get more accurate, if you think about it, the answer would be to simply bring your point in closer. So maybe the point would be at 1.5, 4, and then you would draw a new line. And you can see that is in fact closer to the red line. It's closer to being correct. So then if you continue to bring the 2 points closer and closer together, you should get more and more accurate. So this is how we're going to approach this. We know to find slope, at least up to this point, we needed the slope formula. Okay, well, just for the sake of making this look like they always make it look, instead of using x1 and x2 and then y1 and y2, instead of y1 and y2, we're going to use, I'll leave that there, we're going to use f of x2 and f of x1. Now that's identical, it's just a different way to write it, because f of x is the same thing as y. You still have y values on top and x values on the bottom. Okay, now here's where the big leap is made that makes this look a lot different. So far what we've done is change the y's to f of x. But now, instead of writing x2, I'm going to label this as x1 plus h. Okay, so if you think about it, x1 is a point, and then x1 plus h would be related to x1, but then shifted over a little bit. That plus h gives you what you're shifted over. So it's x1 plus h. So it's not at x1, but it starts at x1 and then is shifted over a little bit, in this case plus h. So when we were using 2, 5, that was really x1 plus 1, because x1 was at 1, so then we added 1 and shifted it over to the right 1. Or when it was 1.5, our h was 0.5, because we were shifting from 1 to 1.5, so we're shifting over 0.5. So instead of writing x2, we're going to write x1 plus h. So I'm going to replace my x2's with x1 plus h. This is still the same thing, it's just a different way to write it. Well, if you notice, now on the bottom we can simplify. And we get this. And we are actually really close to a derivative now. So let's go back to our picture and think about what I talked about. We said that we can find the slope through 2 points. And the closer together those 2 points are, the more accurate our answer will be. Okay, so think about this carefully. If we want the points to be closer together, what is that going to mean for h? As those points get closer and closer together, h should get closer and closer to 0, because the distance, h really represents the distance between the 2 points, and if we make the distance between them 0, then h is going to be approaching 0. So we just talked about limits, and here they are again. The limit as h approaches 0 of f of x plus h minus f of x all over h. And this is the limit definition of a derivative. Now there are some shortcuts you can learn in a couple videos from now that will allow you to bypass this whole big function. But it's important to know that in all of calculus things are based on limits. And this is the way limits relate to derivatives. So, want to make sure you understand, this is written in a triangle because triangles are delta, and delta means change, and that's ultimately what slope and derivative are about, change. This is to help you remember that the derivative is really the same thing as finding the slope at a point or the slope of the tangent line. So these things are interchangeable. They could ask you to take the derivative, they could ask you to find the slope of the point or the slope of the tangent line. They're talking about the same thing in all three of those. So here's an example. Find the slope of y equals 2x plus 3 at x equals 2 using the limit definition of a derivative. Now I know that you can probably just look at that line, because it is a straight line, and figure out what the slope is. But just to start with a simple example, I want to use this. So we're going to use the limit definition of the derivative that I wrote on the previous page, just rewriting it here. And we're going to use that with the function y equals 2x plus 3. So if you look, there's really 3 sections here. I'll color code them. Starting with that red one, it says f of x plus h. What that means is take your function, 2x plus 3, and plug in x plus h. So we get the limit as h approaches 0, 2 times x plus h plus 3. So I took 2x plus 3 and I plugged in x plus h for x. Now my next part says to subtract f of x, my green. So I just subtract 2x plus 3. And the bottom is just h, that doesn't change, so you just divide the whole thing by h. Now if you're in my course, this is as far as I'm ever going to ask you to take this formula, because that's as much as you ever really need to do on the AP test, is be able to just recognize that this is taking the derivative, and specifically it's taking the derivative of 2x plus 3, because you're always subtracting your actual original function. So 2x plus 3 is what we're taking the derivative of. But, so you can see and appreciate the shortcuts when you find them out, I want to go ahead and finish this out. So I'm going to distribute the 2 on top, so I'll have 2x plus 2h plus 3 minus 2x minus 3 all over h. And then 2x minus 2x, 3 minus 3, just leaves us with 2h over h, and we're just left with 2. And the limit as h approaches 0 is just still 2 because there's no h's left. So we knew that from the beginning because that was our slope, but this shows you that this does in fact find the slope at any given point. So let's move on to a more difficult example where calculus is actually helpful. So find the slope of this at x equals 3. So now we have a parabola. So this is all new for us. Unless you've taken calculus before, you've certainly never found the derivative, or the slope on a curve. So we're going to be finding the slope right here at 3. So we start with the limit definition of the derivative. And then I'm going to color code them again to try to help keep us in line. Make sure we all understand what parts are coming from where. So we start with f of x plus h. So I get the limit as h approaches 0, and then I plug x plus h into my function. So I get x plus h squared plus 1 minus f of x. So minus our function, that's x squared plus 1, all divided by h. So x plus h squared plus 1 minus x squared plus 1 all over h. So we took our function and plugged in x plus h, then we subtracted our original function, and we divided it all by h. So I want to pause here again and look at this formula with you. One question you may see on an AP test is they give you this equation that I've got highlighted and ask, what's happening? Well, you're taking the derivative, and specifically you're taking the derivative of x squared plus 1. If you look at the green part, that tells you what you're taking the derivative of. So now let's go ahead and finish this out. You have to FOIL x plus h squared. You get x squared plus 2xh plus h squared minus x squared minus 1 all over h. So then x squareds cancel. Oh, I forgot the plus 1 after the h squared. Sorry about that. Just forgot that plus 1, so I rewrote it there. Plus 1 minus 1 goes away. So I have 2xh plus h squared over h. And I can factor out an h, basically using dividing out, or factoring out. And the h's cancel, and I'm left with 2x plus h. So now what I'm doing is going to take the limit. I'm finally ready. When I take the limit as h approaches 0, you can just use direct substitution, plug in 0 for h, and you're left with 2x. So interestingly, 2x is actually the formula you would use to find the slope for any point on x squared plus 1. But for now, we just want to find it at 3, so all we have to do is plug in 3, and we get our answer that the slope of the point is 6. So going back to our picture here, if we were to draw this tangent line, it would have a slope of 6. Alright, if you're in my course, I just want to make sure you're clear on how far I would ask you to take these. And that's to just plug them in and leave them. So let's look at the limit definition of the derivative. And again, I'll color code it. Now you do need to write the limit as h approaches 0. That is a necessary part of the answer. It's not a derivative without a limit. So first it tells us to take f of x plus h. So we take our function and we plug in x plus h everywhere there's an x. So we get x plus h cubed plus 2 times x plus h. And then we subtract f of x, so we subtract our original function. And we divide the whole thing by h. And for my course, that's as much as you need to know how to do. You can certainly keep going if you want, but we're going to learn some shortcuts that will make all this unnecessary. Okay, so for this last one, start with the limit definition of the derivative. I actually want to show you one thing. Sometimes some books use delta x, so I want to make sure you know that is exactly the same thing. If you see delta x instead of h, it's still the limit definition of the derivative. So we will color code this, make sure we get all 3 pieces done correctly. So first we have the limit as delta x approaches 0. And then we take x plus delta x and plug it into our function. And then we subtract f of x, so we subtract the original function. And we divide the whole thing by h. And And that is the limit definition of the derivative, and it bridges us from limits into derivatives.